Okay, so for chapter 5, I'm just gonna review for a while, yeah,
Yeah.
on on electrolysis. So basically, electrolysis is relating to the electrical conductivity of ionic compounds. And if you can remember from chapter 3, ionic compounds in their solid form cannot conduct electricity because they have no free ions to move around. So unless they are molten meaning melted by reaching their boiling point, or in an aqueous solution referring to water. So it's mixed with water, as water can actually dissolve ionic compounds. And having it in these two forms is the only way you can conduct electrolysis. So now following that, there you already know cations as the positive ions and anions as the negative ones. So the cathode attracts cations because they both start with cat, so you know they attract each other. Anodes attract anions. So since cations are positive ions, we know that cathodes are negatively charged because opposite attracts. So if you have a positive and negative ion, they will attract together. That's basically how an ionic compound works, and it's the same thing in electrolysis. So if you have negative and negative, they will not attract each other. They will actually repel. So that's basically the difference. So moving on to the second part. The first example in our book, if I'm not mistaken, is the electrolysis of lead bromide. So for lead bromide, lead is Pp and bromide is the diatomic form of bromine. So the method to do this is to first add the lead bromide. The number 2 in here, this part, it refers to the valency. So lead can receive it can give away 2 electrons to bromine. That's why lead bromide is a compound. And if you remember, bromide is in group 7, which means it can receive 1 electron. So following that, we need to add 2 graphite rods as the electrodes. The electrodes are the cathode and anode I mentioned earlier. And we need to turn on the power pack or battery and allow electrolysis to take place. So basically, as you can see here, there is a battery. This is the battery, the small 2 lines. Wait. And the longer side, the longer one is positively charged, and the shorter one is negative. That's why you can see this one is negative and this one is positive. So the cathode, since it attracts cations, which means metals will form here, but at the anode, it will be non-metals. So the lead ion gains 2 electrons at the negative cathode. So basically, since they're attracted here, they will get electrons from the bromide ions. So each bromide ion, so as you know, lead bromide is actually already balanced. When they are attracted to the cathode and anode respectively, it's because of their charges. For example, lead is a metal, so it gives away electrons, right? Now, when it gets attracted to the cathode, the electrons will be pulled upwards to the other side of the circuit. So the metals will eventually get the electrons from the bromine because the bromine will lose their electrons. So their charges will be neutral and they will form into the original compounds as singular. So at the cathode, you'll have solid lead, while at the anode, you'll have bromine, sorry. So the expected result from the electrolysis of lead bromide is that the bromide ions move to the positive electrode, the anode, So basically what I explained earlier, there is bubbling at the anode as brown bromine gas is given off. So if there is a detail about brown gas forming in the lead bromide electrolysis, it's bromine. And the positive lead ions move to the negative electrode, which is the cathode, and gain electrons to form a gray lead metal. So following that, the first example, this lead bromide, is actually very simple. So the next example will be a bit more complicated, the next few. So the next one is aqueous sodium chloride. So as you know, aqueous refers to a water solution. So sodium chloride, when put mixed with water, it dissolves and turns into a liquefied form. Because sodium chloride is basically salt. And since salt is solid, it cannot conduct electricity. Now, if you see the word brine, this word, brine is a concentrated solution of aqueous sodium chloride. So if you see this word, it's referring to sodium chloride. It can be electrolyzed using inert electrodes. Electrodes are the electrodes, the cathode and anode respectively. So electrodes are usually made from inert elements like platinum, carbon, or graphite, things that don't react, that are not very reactive, because if they are very reactive, later the products we get will change, which is something we don't want. So when electrolyzed, sodium, it produces bubbles of gas at both electrodes as chlorine and hydrogen are produced. Now, as you know, at the cathode, like I said earlier, metals will be produced here, right? But why is hydrogen produced? So to answer that question, where is it? Wait, I lost it. Here. So in electrolysis, there is a reactivity table, essentially. The exceptions here that are not metals are hydrogen and carbon. But in aqueous, as you know, water is H2O. And when mixed with an ionic compound, it becomes H plus and OH minus. H plus is hydrogen and OH minus is a hydroxyl group. So the least reactive metal will be electrolyzed, as you can see, sodium is one of the most reactive and hydrogen is much less reactive. So hydrogen will actually be electrolyzed instead of sodium. That's why there's hydrogen here. And as for chlorine, because it's a group 7, group 7s are always going to be electrolyzed. And following that, a similar example to this is dilute sulfuric acid, H2SO4. But the difference here is, so like before, it's also hydrogen at the cathode, because the metal in there isn't exactly a metal in sulfuric acid, because it's a covalent bond. H hydrogen is a non-metal, sulfur is a non-metal, oxygen is also a non-metal. So they share their electrons. And basically to follow that, wait. In the reactivity table, as you can see, the only thing that can be electrolyzed on the cathode is hydrogen. So what forms in the cathode is still hydrogen, but for dilute sulfuric acid, it's also hydrogen, but for the anode, SO4 is sulfur oxide essentially, but it's not a group 7 element. But if there is no group 7 element, this is an important rule, what will be electrolyzed will be the OH group. That is in aqueous solutions. So the sulfur and the oxygen will not be electrolyzed. And there is actually a way to test for the gas produced. Like for example, if the gas produced at the anode, you can test it by relighting a glowing splint, which is essentially to light the stick on fire. And you can dip it into a test tube to test for the gas. And if the gas produced at the anode bleaches damp litmus paper, then the gas is chlorine. So litmus paper is used to test for certain substances. If if the litmus paper turns white, then you know it's chlorine. And for hydrogen, it's produced at the cathode because it's different from the other nonmetals. So if the gas produced at the cathode burns with a pop when the sample is lit with a lighted splint, it's different. The gas is hydrogen. So following that, this is the reactivity table. I'll send this to you. So for aqueous solutions will always have water, H2O, what I said earlier, but you can visualize it like this. So this means reversible. So you can turn H2O water into hydrogen, positive hydrogen ions, and negative OH, which is hydroxyl. Because you can see H2, there's one H here, and there's another H here, and there's one O. So these ions are also involved in the process and their chemistry must be considered. We now have an electrolyte that contains ions from the compound plus ions from the water. For anions, the more concentrated ion will tend to get discharged over a more dilute ion. This is referring to the positive electrode or the anode. So for negatively charged OH minus ions and nonmetal ions, they are attracted to the positive electrode, the anode. But if halide ions, halide is referring to halogens or group 7, like chlorine, bromine, iodine, and OH are present, it will be the halides or the group 7s. Like earlier, with dilute sulfuric acid, if you still remember before, it's H2SO4. There are no group 7 elements in there as individuals. So that's why the OH group is the one getting electrolyzed. And that is the basic reason. And going further with that, this example can be skipped. So now, so this is a basic table of aqueous solutions. So concentrated sodium chloride, NaCl. So at the anode, of course, chlorine is group 7, so it's released. And at the cathode, it's hydrogen gas. And concentrated and dilute is different, as dilute means if it's a dilute sodium chloride solution, it means there is more water than there is sodium chloride. But in concentrated, there is like a near equal amount. So for dilute sodium chloride, the product at the anode is oxygen. And this oxygen, why is it not OH, right? Well, technically, OH or hydrogen is basically oxygen and hydrogen is normally at the cathode. So at the anode, it's just oxygen if it's dilute, because there's more water than there is sodium chloride. And at the cathode, of course, it's still hydrogen because sodium is very reactive. And for concentrated aqueous copper sulfate, as I mentioned earlier, sulfate, SO4, is not group 7, so it's oxygen again. And for the cathode, copper is lower than hydrogen in the reactivity series, so copper is preferentially discharged as a metal. So it's not hydrogen this time because, well, the table earlier is actually very important. You can see copper is under hydrogen. So that's why copper is electrolyzed. And for dilute sulfuric acid, which I mentioned earlier, oxygen gas is released at the anode because, yeah, SO4 or sulfate is not group 7. That's the general rule. And at the cathode, it's hydrogen because, well, there's no metal in the compound. Okay, so Following that, let's see. Next is electroplating. For electroplating, it's basically covering up another object with a certain type of metal, which includes silver, copper, and many others. So the anode is made from the pure metal you want to coat your object with. So, for example, you want to make something shinier, more pretty, or more attractive. So you want to make a spoon shine like gold. Then at the anode, you will put the spoon. The pure metal here refers to the spoon in its original state. And the anode is the substance you want to cover your object with, and the cathode is the object to be electroplated. So the cathode will be the spoon. And for example, you want to coat it with gold. So your anode would be gold. And your electrolyte is an aqueous solution of the soluble salt of the pure metal, the anode. So let's just change this to copper. So the electrolyte would be copper. The electrolyte would be made of copper sulfate. Now, we use a copper salt because we want to coat it with copper. And gradually, as electrolysis occurs and the spoon gets coated with the copper, the electrode will start shrinking. And to avoid it from completely disappearing, we use the copper sulfate will keep it in shape and continue compensating for the loss of copper as the spoon gets coated. So another example is coating a strip of iron metal with tin. So in this case, they use tin chloride as the electrolyte. At the cathode, they have a strip of iron metal, and at the anode, they have a strip of tin metal because it's so like earlier, the substance they want to use to coat something is on the anode, and the substance that is getting coated is at the cathode. So electroplating is also done to make metals more resistant to corrosion or damage so they don't break as easily. Like examples, chromium and nickel plating. And it can also be done to improve the appearance, like coating cutlery and jewelry with silver. Following that, we have hydrogen fuel cells. Hydrogen fuel cells are a sustainable, eco-friendly way to make electricity, and the only waste product they release is water. So how it works essentially, first the fuel in, as you can see in this yellow arrow, it's hydrogen. The hydrogen here will get split by a catalyst into a proton and electron. As you know, hydrogen has an atomic number of 1 because it only has a proton, no neutrons, but it does have 1 electron. Now, there is a PEM membrane, proton exchange membrane. So hydrogen is split into a proton and electron. The proton part will pass through this membrane to the other side, through here, the electrolyte. But the electrons will have to pass through the circuit as it is negatively charged, and the PEM, proton exchange membrane, only accepts the positive one. So it will go through the circuit, generating electricity here, and then it will combine back with the hydrogen in the electrolyte. And the hydrogen and oxygen bonds together, creating water, and it is released. So it's basically just electricity and water. It's a very simple process, and it looks something like this. So hydrogen is split into positive hydrogen ions and electrons. There are 2 electrons because there's 2 hydrogen. And for oxygen, they gain 4 electrons and they form -2 oxygen, basically. So the overall equation, if you are asked for the word equation, is hydrogen plus oxygen reacts to form water. You don't have to mention electricity in the word equation, but you just basically have to know the process that hydrogen is split into proton and electrons and how electricity is formed. And that is, oh wait. And lastly, the last part for the chapter 5 review is the advantages and disadvantages of hydrogen fuel cells. So, hydrogen oxygen fuel cells are becoming more common in the automotive industry to replace petrol or diesel engines because they are more sustainable. And unlike diesel powered vehicles, which release carbon dioxide and carbon emissions, hydrogen fuel cell powered cars or machines will release water. If heated, it will release as water vapor, which is not harmful whatsoever. So the advantages are they do not produce any pollution. The only product is water, whereas petrol engines produce carbon dioxide and oxides of nitrogen. They release more energy per kilogram than either petrol or diesel, and no power is lost in transmission as there are no moving parts, unlike an internal combustion engine. Also, it's quieter, so less noise pollution compared to a petrol engine, because as you know, the sound of cars is heard very easily because of how loud it is. But it comes with some disadvantages, such as the materials used are expensive. That's why there isn't a lot of hydrogen fuel cells now, because the price to make one itself is quite pricey. And hydrogen is more difficult and expensive to store compared to petrol, as it is very flammable. So if you heat up hydrogen just a bit too much, it may explode. Next, fuel cells are affected by low temperatures, becoming less efficient. So you need to control the temperature. If it's too low, it may not function properly, but if it's too high, it may combust or explode. And there are only a small number of hydrogen filling stations across the country, and hydrogen is often obtained by methods that involve the combustion of fossil fuels before releasing carbon dioxide and other pollutants into the atmosphere. And that's it for chapter 5. Do you have any questions?
No.
Okay, so let's move on to chapter 6, yeah?
Yeah. Wait. Can you enable screen share?
Oh, yeah, sorry. Yeah, okay. Wait. Does it work?
Wait. Yes, it works. Okay, so this is my presentation about chemical energetics. Petroleum oil refining. Or crude oil is a complex mixture of compounds known as hydrocarbons, which are the molecules that contain only the elements hydrocarbon and carbon are bonded together covalently. Petroleum is not only a major source of fuel, material of enormous, but also a raw material of enormous importance. It supplies a large and diverse chemical industry to make dozens of products that we use in everyday life. For example, oil refining creates polymers and medicines. Petroleum is not very useful to us. It's not very useful to us until it has been processed. The process known as oil refining. Oil refining is carried out at an oil refinery. Refinery involves separating petroleum into various batches or fractions. Chemists use a technique called fractional distillation to separate the different fractions at the oil refinery station. The different fractions separate because they have different boiling points. The petroleum is heated to about 400 degrees Celsius to vaporize all the different parts of the mixture. The mixture of vapors passes into the fractionating column near the bottom. Each fraction is obtained by collecting hydrocarbon molecules, which have a boiling point in a given range of temperatures. The liquids condensing at different levels are collected on trays. In this way, petroleum is separated into different fractions. The process is known as fractionation. The properties of the fractions obtained from this fractional distillation change from the bottom to the top of the lower with lowering boiling points, higher volatility, lower viscosity, and decreasing chain length. Fossil fuels. A fuel is any substance which can be conveniently used as a source of energy. Fossil fuels release energy in the form of heat when they undergo the process of combustion. So fossil fuel plus oxygen equals to carbon dioxide plus water plus enthalpy change of heat. The perfect fuel for fossil fuels will be cheap. It is available in large quantities, safe to store and transport around, easy to ignite and burn, causing no pollution, release no greenhouse gases, which is good for the environment, and capable of releasing large amount of energy. The alternative sources to fossil fuels. Fossil fuels are an example of non-renewable resources because they are not being replaced at the same rate as they are being used up. It is important to use non-renewable fuels very carefully and to consider alternative which is renewable sources of energy for use now and at the future, including nuclear fuel, hydroelectric, biomass and biogas, hydrogen, wind, tidal, wave, geothermal, and solar. Exothermic and endothermic reactions. An exothermic reaction transfers thermal energy to the surroundings, leading to an increase in the temperature of the surroundings. So the thermal energy in the surroundings will increase because of exothermic reaction. And an endothermic reaction takes in thermal energy from the surroundings, which leads to a decrease in the temperature of the surroundings. So the thermal energy will decrease if endothermic reaction. Exothermic reactions. We obtain exothermic reactions. We obtain exothermic reactions from the combustion of fuels. When natural gas burns in a plentiful supply of air, it produces a large amount of energy. Methane plus oxygen equals the carbon dioxide plus water plus enthalpy change of heat. CH4 plus 2O2 equals to CO2 plus 2H2O plus enthalpy change of heat. During the exothermic reaction process, the complete combustion of the methane heat is given out. So it is an exothermic reaction. Endothermic reaction. There are also reactions which take in thermal energy, and these energy are known as endothermic reactions. When an endothermic reaction occurs, energy is taken in from the surroundings and the temperature of the surroundings decrease. So for example of endothermic reaction is when a cold pack is used to treat a sprain when you're injured. The cold pack contains an inner bag of water and a chemical which will react with it to produce an endothermic reaction. So this is the diagram of exothermic and endothermic diagrams. As you see, the exothermic reaction, which is enthalpy change of heat negative. So the heat goes down and heat is released to the surroundings. And then for endothermic diagrams, endothermic reaction is this one on the right. And then enthalpy change of heat is positive, so the reactants will go up to products and the heat absorbed from the surroundings. So what is enthalpy change? Enthalpy change is the energy stored in the bonds, and the symbol for enthalpy change is H, which is heat. The transfer of thermal energy during a reaction is called the enthalpy change of reaction, and it is shown as enthalpy change, or known as delta H. For an exothermic reaction, enthalpy change of heat is negative, and for an endothermic reaction, enthalpy change of heat is positive. Activation energy. So activation energy is when fuels such as methane are burned. They, they require energy to start the chemical reaction. This energy is known as the activation energy, or known as EA. So activation energy, or EA, is the minimum energy which is needed to allow the colliding particles in the reaction mixture to form products. Here's the diagram of exothermic reaction pathway. In an exothermic reaction, the reactants are at a higher energy level than the products, which is this one, above the line. The energy released during the reaction of enthalpy change of heat is negative and represented by a downward arrow between the line, and the activation energy is the minimum energy required for the reaction to proceed and is shown as a hump on top of the line between the reactants and the products. So it is parallel with the line. It is between the reactants and products. Endothermic reaction pathway diagrams. So this is the reaction pathway diagram for endothermic. And at endothermic reaction, the reactants are at a lower energy level than the products. The energy absorbed during the reaction, delta H, is positive and represented by an upward arrow on top of the line in the reactants. The reactants will go up the products. The activation energy is the minimum energy required for the reaction to proceed and is shown as a hump between the reactants and the products. When any reaction occurs, the chemical bonds in the reactants have to be broken, and this require this requires energy, and this is an endothermic process. When the new bonds in the products is formed, energy is given out, and this is an exothermic process. So when the energy is given in is called endothermic process, and when the energy is given out is called an exothermic process. The enthalpy change of a reaction is the difference between the energy required to break bonds and the energy given out when bonds are made. So for the question, the table below shows bond energy data for a series of covalent bonds. This is the bonds. So number 1, use the information given in the table to calculate the overall enthalpy change for the combustion of ethanol producing carbon dioxide and water. We're gonna do question 1 first. So for the answer of number 1 is C2H5OH plus 3O2 equals to 2CO2 plus 3H2O. This is the diagram. When breaking, C H equals to 5 times 435. So where I get the 5 from the H5 here, I put the 5 here times 435 equals to 2175. And for CO is 358 and OH is 464. O OO equals to 3, which I get from the 3 in up here. 3 times 497, which is the O equals to 1491. So for the total of the bonds is 2175 plus 358 plus 464 plus 1491. So we add all of these up and it equals to 4488 kilojoules of energy. So for the bond making is CO equals to 4 times 803.
Got juga ya.
Wait, let me find the... Okay, so the answer for number 1 is C2H5OH plus 3O2 equals to 2CO2 plus 3H2O. So the breaking process is CH equals to 5 times 435. I get the 5 from H5 here. And it equals to 2175. CO equals to 358. OH equals to 464. And OO equals to 3 times 497 equals to 1491. So the total is 2175 from CH and then plus the CO and the OH, which is 358 plus 464 plus the result of OO, which is 1491, which equals to 4488 kilojoules of energy. For the bond making process, C equals to O equals to 4 times 803, which is 3212. And HO equals to 6 times 464 equals to 2748. 2784. So for the 4 that I get here is 2 times 2 and the 6 is 2 times 2. So for the total, we're gonna total CO and HO. So for the total of CO is 3212 plus the total of HO, which is 2784. And this equals to 5996 kilojoules of energy.
Well, ito, can you go
Answer
back
for
for a
number
while?
2. What?
Can you go back for a while?
Okay. Yep,
Yeah, this one,
I did.
for the bond breaking, you forgot the CC bond because ito kan ada carbon.
The carbon. Oh yeah. I forgot
Then,
CC.
yeah, just making sure.
Okay. What else?
Yeah, that's it, ko. I just want to let you know.
Okay. I will proceed to the next one.
Yeah.
So for the answer of number 2 is enthalpy change is heat equals to bond breaking minus bond making, which is 4488 minus 5996, which is negative 1508 kilojoules per mole of ethanol burned. So the process in number 1 is exothermic because the enthalpy change is negative because the total is negative. Because the total when we add this is negative. So the enthalpy change is negative. Thank you. Thank you for listening.
Okay, so I'll move
Just
to
go to
chapter
yours.
7, yeah. Wait,
Yeah.
where is it? Wait.
Is there any question?
No, your presentation is clear. Okay.
Only for the CC one,
Yeah,
right?
that's it. I just need you to change that so you don't get it wrong, Chuka.
Okay.
Okay, so for chapter 7, it's a bit long, but I'll try to shorten it a bit. So it's about chemical reactions. So in chemical reactions, there are two types of changes happening, which are physical changes and chemical changes. Physical changes, such as melting or evaporating, do not produce new chemical substances. You can reverse them, like how you can turn water into ice, but you can still melt back ice to water without changing anything chemically. Making a mixture from two or more substances or dissolving a solute in solvent are examples of physical changes. For example, when you mix salt and water together, when you stir that, the salt will dissolve, but if you heat up the solution of salt and water, the water will be separated from the salt again, and you will get back the salt you dissolved earlier. Now, for chemical changes, or sometimes referred to as chemical reactions, new chemical substances are formed that have very different properties to the reactants. There may be signs that a new substance has formed, such as color change. An example of color change that often happens is like when you cook food, for example, when you cook chicken, it starts out as a pinkish red color, but after you finish cooking it, it turns white. Yeah, that's an example. You can't turn the chicken back raw anymore, so that's an example of a chemical change. A precipitate being formed. Now, precipitate refers to like a cloudy substance. Next, bubbles of gas. Bubbles of gas, different types of gases can be formed depending on the reaction. And most chemical reactions are very difficult to reverse. Some can be, but very few can actually be reversed. And energy changes also accompany chemical changes, and energy can be given out exothermic or taken in endothermic, like the topic you just explained before. So the majority of chemical reactions are exothermic, with only a small number being endothermic. So for the factors that affect these, first there is the concentration of reactants or solutions and the pressure of reacting gases. So as you can see on the side, I have a graph showing the amount of products in both reactions being the same, but the reaction rate is different. So the higher the concentration, the increased pressure of gas, the reaction will increase. As you can see the pink line here, it had a higher increase much faster compared to the green one because the green one had a lower concentration and lower pressure. Next, temperature at which the reaction is carried out. As you remember from kinetic particle theory, the higher the heat, the faster the particles. Surface area of solid reactants, which I will explain soon, and the use of a catalyst. Catalysts are substances that speed up chemical reactions by reducing the activation energy needed to start a reaction. So changes in these factors directly influence the rate of a reaction, and it is important economically to have a higher rate of reaction as this implies a higher rate of production and a more efficient process as well. As if the activation energy is too high, it will be over demanding of resources and will not benefit humankind. So just to explain one of the graph I showed you earlier, the concentration and pressure, compared to a reaction with a reactant at a low concentration, the graph line for the same reaction but a higher concentration or pressure has a steeper gradient, so it has a higher increase compared to the decreased concentration. Moving on, I'll present the other factors. So for the surface area, So to increase surface area, you have to make it smaller. So if you have a chunk of sodium chloride and powder of sodium chloride, the powdered one will have larger surface area. Similar to how our intestines have a lot of villi and microvilli to minimize surface area, powder has a higher surface area as there's more for the solutions to act on. And as you can see, the pink line once again shows the powder when it reacts in a chemical reaction compared to the green one, which is lumps or big groups of them, such as solid form, like big chunks of them. It's slower as there's less surface area to act on. Next, for temperature, the higher temperature has a faster increase because of, well, kinetic particle theory. The temperature is relatively simple. It's just dependent on how hot it is. And catalysts. So just note that catalysts are substances which speed up the rate of reaction without themselves being altered or consumed. So even after they take part in the chemical reaction, they won't be changed or finished. They can still be used. As you can see, without a catalyst, the green line, it's much slower compared to the pink line where you use a catalyst. So moving on. Next is collision theory. Collision theory states that in order for a reaction to occur, the particles must collide with each other. The collision must have sufficient energy to cause a reaction or enough energy to break bonds. And the minimum energy that colliding particles must have to react is known as the activation energy, which you explained earlier. So the diagram here, the one at the top, it says unsuccessful collision because you can see on the right side, nothing has changed. It's still the same. But underneath it, it shows a successful collision where the molecules were altered somehow. As you can see, the original double bond of this molecule eventually changed into singular ones. So to follow on, collisions which result in a reaction are known as successful collisions, this one, if they have sufficient energy. Great. So it can be greater or equal to the activation energy and they will react. The collision will then turn out to be successful like this one. But not all collisions result in a chemical reaction. Most collisions just result in the colliding particles bouncing off each other. Like an example is in the air, although there are many types of gases, they don't all collide with each other and combine to change. They just bounce off each other, which similarly to what we learned in physics. And collisions which do not result in a reaction are known as unsuccessful collisions, like the one at the top right. Unsuccessful collisions happen when the colliding species or the particles do not have enough energy to break the bonds. So, increasing the number of successful collisions means that a greater proportion of reactant particles collide to form product molecules. So, this refers to the more collisions that are successful, the more we can make. And the number of successful collisions can depend on the number of particles per unit volume. So, volume is in cubic centimeters, assuming you have 24 cubic centimeters and there are 24,000 particles. Compared compared to having only 12,000 particles, you will have a much higher rate of successful collisions if you have more. The frequency of collisions. This can be altered with heat or pressure, with more heat and more pressure applied, making the particles move faster, which increase the rate of kinetic energy, and following that kinetic energy of particles, which is similar to the frequency of collisions, and the activation energy. Fewer collisions will have an energy that exceeds higher activation energy, and fewer collisions will be successful. So you need to actually beat the activation energy, and this actually may need a lot of energy. To give a follow-up, an example of a substance that decreases the activation energy needed is cryolite. That is one of the few examples. So to follow that, so for temperature, it'll increase the rate of reaction because there's more kinetic energy, and you can see it here. When you increase the temperature, they'll collide more often because there's more heat there compared to the less temperature, where as you can see, the particles are not moving as fast. And then next, this one is concentration. There are only three types of each three of each particle. There. Meanwhile, here it's quite crowded with a lot of them. It's more concentrated, so it's more likely for them to collide with each other. Next, this is referring to the surface area. So as you can see, reactant 1 here is the pink one, is a big chunk, right? So it's hard for it to break apart and to collide with just one. And if you only have one giant lump like this, you won't be able to have successful collisions. But if you break down reactant 1 into multiple pieces, it'll increase the surface area, allowing for more successful collisions. Following that, catalysts, which I mentioned earlier. So catalysts at the beginning, at the end, will still say the same. And basically, they work on the same principle, providing a different pathway for the reaction to occur that has a lower activation energy. So this means a higher proportion of the reactant particles have energy greater than the activation energy and will result in more successful collisions per second. Now, in our book, later you get on page 106, there are examples of catalysts, which is important for tomorrow, and you should probably memorize them. There's only 4 of them, and you should just try your best to understand them. So one of the examples is iron, which is for the Haber process, as mentioned in our book, the Haber process for ammonia, which I will mention later. It speeds up the process and decreases the activation energy needed. Now, enzymes are biological catalysts. The difference between the ones we use here and biological ones are that we have biological catalysts in our body. As you can see here, the reactants and the products, the reactants have energy that goes above the activation energy needed. But lower activation energy is shown by the red broken lines after using a catalyst. Okay, so following that, wait. Next is investigating the rate of reaction. So there are a few ways we can do this. So we can check that the proportion to the concentration of the reactant of a product, like color, mass, volume. Faster reactions can be easier to measure when the reaction is over by averaging a collected measurement over the course of the reaction. Some reaction rates can be measured as the reaction proceeds. So this sounds a bit complicated, but to sum it up, you can do this by measuring mass, the difference in mass on a balance or a weighing scale, measuring the volume of gas produced, and measuring a reaction where there is a color change at the end of the reaction. You can also follow up by investigating the effect of surface area on the rates of reaction. So you can see an example here with dilute hydrochloric acid. They add calcium carbonate chips, and the reason they use chips is to increase the surface area for the hydrochloric acid to add on. And as you can see, there is gas produced. It passes through the capillary tube to the other side where gas collects. And as you can see, different forms of them can alter the results, and we can measure those. So following that, the method choice, disappearing cross experiment. It is a simple experiment with no specialist equipment required, but actually for the method choice, you don't really need to know these. It's just something I put if you want to learn them, but for the sake of saving time, I'm going to skip them for now. And let's move on to the next part, which is wait, sorry. Which is the concept of equilibrium. Equilibrium refers to balance, basically. So during the course of a reaction, the rate of the forward reaction equals the rate of the reverse reaction. So if this does happen, the overall reaction is said to be in a state of equilibrium or balance. So equilibrium is dynamic. Example, the molecules on the left and right of the equation are changing into each other by chemical reactions constantly and at the same rate. The concentration of reactants and products remains constant. They will not change. And it only occurs in a closed system so that none of the participating chemical species are able to leave the reaction vessel. So equilibrium can only be reached in a closed vessel, which prevents reactants or products from escaping the system. So as long as you are in a closed system, no outside products will affect the achievement of equilibrium. So this shows the difference. So in an open system, the iodine can actually escape, but in a closed system, it maintains the concentration. So as you can see here, there is an arrow which shows that a solid iodine can turn into its gaseous state, but it cannot turn back. But if you put it in a closed system, you can actually turn it back into its solid state. So an example, so to further explain this, uh, uh, an, an example is the reaction between hydrogen and nitrogen in the Haber process. When only those two are present at the beginning of the reaction, the concentration of the two are at their highest. As the reaction proceeds, the concentration of both hydrogen and nitrogen slowly decrease, and the rate of the forward reaction will decrease. But the concentration of ammonia is gradual. If you didn't know, ammonia is NH3, and well, the rate of backward reaction will increase as ammonia will decompose to reform hydrogen and nitrogen. Since the two reactions are interlinked and none of the gas can escape, the rate of the forward reaction and the rate of the backward reaction will eventually become equal. And you should know how to balance it. 3H2 plus N2 in forward reaction forms or reacts to form 2 ammonia, and 2 ammonia can be decomposed to form 3 hydrogen and nitrogen. So this diagram shows the rates of forward and backward reaction when they become equal. So the forward rate reaction will decrease and the reverse rate increases. So this makes them the same and equal. Okay, so following that, so the effect of temperature on equilibrium. So an increase in temperature, equilibrium moves in the endothermic direction to reverse the change. And a decrease in temperature, equilibrium moves in the exothermic direction to reverse the change. Example, iodine monochloride reacts reversibly with chlorine to form iodine trichloride. So when the equilibrium mixture is heated, it becomes dark brown color. You can use this observation to deduce whether the backward reaction is exothermic or endothermic. Equilibrium has shifted to the left as the color dark brown means that more ICl is produced. So increasing the temperature moves the equilibrium in the endothermic direction, so the backward reaction is endothermic. So backward refers to ICl3 going to ICl and Cl2. Next is the effect of pressure. Increase in pressure means equilibrium shifts in the direction that produces the smaller number of molecules of gas to decrease the pressure again. So it's attempting to maintain the pressure by decreasing the production of molecules. And when the pressure decreases, a larger number of molecules of gas is produced to increase the pressure again. Lastly, I think this is the last for the factors. An increase in equilibrium concentration will actually cause equilibrium to shift to the right to reduce the effect of increase in the concentration of a reactant. but a decrease in concentration will cause equilibrium to shift to the left to reduce the effect of a decrease in the reactant or an increase of the concentration of the product. So an example is nitrogen dioxide can form dinitrogen tetroxide, a colorless gas. So to predict the effect of an increase in pressure on the position of equilibrium, the number of molecules of gas on the left, you start out with 2, number of molecules of gas on the right, 1, and an increase of pressure will cause equilibrium to shift in the direction that produces the smaller number of molecules of gas. So equilibrium shifts to the right and the reaction mixture becomes paler as more colorless N2O4 is produced. So to briefly explain the effect of a catalyst on equilibrium, the presence of a catalyst does not affect the position of equilibrium, but it does increase the rate at which equilibrium is reached. So if you use a catalyst, you can get equilibrium faster. Following that, I'll just explain for catalysts, I've explained this part earlier. And now let's move on to the last few parts. We just need the Haber process and the contact process. So for the Haber process, ammonia is made here, ammonia NH3. So essentially, it's just H2 and N2 obtained from natural gas. The gas are compressed to about 200 atmospheres. So this is the amount of pressure required for this process. And 200 atmospheres is like 20,000 kilopascals. And the pressurized gases are pumped into a tank containing layers of catalytic iron beds. Iron is a catalyst for the Haber process. You can check this on page 106 of the chemistry book. And some of the hydrogen and nitrogen react to form ammonia. But the unreacted hydrogen and nitrogen pass into a cooling tank. The ammonia is liquefied and removed to pressurized storage vessels. And the unreacted hydrogen and nitrogen gases are recycled back into the system to make it over again. So this is essentially the process. Hydrogen and nitrogen, they get compressed, form the ammonia, and they repeat the process. Okay, so next is to finish up on the Haber process. Reaction conditions such as temperature, pressure affect the rate of reaction. If the reaction is reversible, then the position of equilibrium is also affected by changes in these conditions, and we must often consider a trade-off between the rate of reaction and production yield. So the graph below, this one, shows the effects of changing temperature and pressure on the yield of ammonia obtained. By following the curved lines, it can be seen as the pressure increase, so too does the yield of any given temperature. So as you can see here, as temperature is increased, it happens fast. The yield of ammonia is actually decreased. But when you have a lower temperature, the yield of ammonia is increased. And for the yield of ammonia produced, so economic considerations are related to goods and selling for profit. And the availability and cost of raw materials is a major consideration, which must be studied well before they actually decide to produce these. So the production energy costs are also a factor to be considered carefully and alongside the raw materials issue. The temperature of 450 degrees Celsius, which means a higher temperature, would favor the reverse reaction as it is endothermic, and which means it takes in heat. So a higher yield of reactants would be made. If a lower temperature is used, it favors the forward reaction as it is exothermic, so a higher yield of products will be made. However, at a lower temperature, the rate of reaction is very slow. You already understand from kinetic particle theory. And the pressure used is 200 atmosphere. So a lower pressure would favor the reverse reaction, and a higher pressure would favor the forward reaction, similarly to the one above. But basically flip. So for the catalyst, iron. So the iron will speed up the process by decreasing the activation energy required. And that is basically the Haber process. Next, I think, yes, the contact process. So sulfuric acid is made by this process. As you can see, S plus O2 reacts to form SO2. So the main stage in the contact process is the oxidation of sulfur dioxide to sulfur trioxide by using vanadium oxide, V2O5, which is the catalyst for this process. So 2SO2 plus O2, rightwards harpoon over leftwards harpoon, 2SO3. The oxygen used in this stage is obtained from the air. The conditions for this main stage of production are a temperature of 450 degrees, a pressure of 2 atmosphere or 400 kilopascal, and once sulfur trioxide is formed, it undergoes more processes to form sulfuric acid. So an exam tip is you need to recall the temperature, pressure, and catalyst needed for contact process and the equation for the main stage only, which is this. You can actually find this also in the book on page 111. So explaining the conditions needed for contact process. Basically, the forward reaction is exothermic, so increasing temperature shifts the position of equilibrium to the left. So the higher the temperature, the lower the yield of the sulfur trioxide, like the one we learned earlier for this, but the difference is the lower the temperature, we get a higher percent yield of ammonia. But for the contact process, a higher temperature will give a lower yield instead, which is basically the same. As you can see, a higher temperature gives a lower yield. Following that, an increase of pressure shifts the position of equilibrium to the right, but the position of equilibrium lies far to the right as the equilibrium mixture contains about 96% sulfur trioxide. So the reaction is carried out at just above atmospheric pressure. And that is it for this chapter. Do you have any questions?
No. Is my words clear before when I
Yeah,
present it?
it's clear, it's clear.
Okay. Is it too fast or too slow? Maybe.
Nope, it's fine. Was I too
Okay.
fast with the presentation?
No,
Okay,
it's not fast.
so we'll end it here, yeah.